start with a proof. We're going to do 3 days of compound angles. And I'll give you a bit of context of what that of what their purpose is. Okay, they are going to end in some identities. So after we've done compound angles, this is the first new grade 12 stuff that we can add in as new identities and solve some new identities. So I think Monday next week we'll be doing some identity work again. But we're going to do 3 days of compound angles. So today we're going to look at cosine, tomorrow sine, the next day tan. We're going to look, and their formulas. The formulas are in the notes, so you'll see the formulas for all of them, but we're going to only do cosine questions today. And the reason why, when we calculate exact values, we have a very small limit of angles we can use to calculate them. So somebody give me an example of one of the angles that we can calculate the exact value of. Pi over 4, right? So 45 degrees, that's in our special triangles. Very good. What else? Pi by 6, pi over 6. What else? Pi over 3. Pi over 3. And then pi, 2 pi, pi by 2, 90 degrees, 180, 270. Like all those ones as well, we can get the exact value of in different ways. But that's it. Of all the angles that there are, those are the only ones that we can do, right? So like basically 3 angles per quadrant. Not that many. Compound angle formulas allow us to do that for a lot more angles. So that's sort of the quick summary of what we're going to get out of this. But it ends up being a bunch of new formulas that you do have to memorize 100%, and a little bit of sort of algebra or mechanics that we need to practice. But it ends up being, again, kind of repetitive. Once you've done it a few times, you should be able to get the hang of it. Okay, so here, let's take a look at this diagram. We're going to do the proof or the derivation of 2 of the compound angle formulas. There's 2 for cosine, so we're going to look at those. And I always wonder if the first derivation that you really do is it comes in grade 10 when you look at the quadratic formula, right? Do you remember deriving that in grade 10? Like not that you have it memorized, but do you remember at least sitting in class while it was happening? Anybody? Does anybody remember how the basics of how the quadratic formula is derived? No? It is a little bit long. You just take ax squared plus bx plus c and complete the square with a little bit of simplifying, right? You just basically do completing of the square with variables and move things around so they look nice, and you get the quadratic formula. Anyway, and then you probably did sine law and cosine law as well. So you would have seen the derivation. I think most of you would have seen the derivation of those 2 formulae at some point. And I always wonder if high school students are like, how in the world are we supposed to be able to do that? Like, where does that come from? I could have never figured that out. How do you know? How would you know to do that? So you probably wouldn't. And even really, I might not, except that I've done it a bunch of times. So I have the little tricks or the little important steps memorized. Like I know what's coming next. I know the steps in advance. In that case, it's very reasonable that you would be able to do any of those. Your algebra skills should be good enough that you could complete the square, especially with a little bit of practice, using variables, and derive the quadratic formula. That shouldn't be outside your capabilities, especially after we do a little bit more algebra in the polynomials units in this course. Okay, it wouldn't actually be that hard for you. It's just knowing what to do. So how would you know that this is the right diagram to start with, or how would you know? Like we're going to do two sort of important things, and the rest kind of falls into place. How would you know to do that? You wouldn't, unless somebody showed you. But once somebody showed you once, you could kind of remember, oh yeah, right. You do that, and then a little bit of algebra, the rest falls into place. Okay, so when you're just being introduced to these derivations, I would say that's the position that you're in. You need to memorize a few key steps, and the rest of it you could probably figure out. The people who figured it out originally sat for hours and hours and hours trying a lot of things that didn't work until eventually, eureka, aha, they had a moment where they thought about some connection and then, again, probably worked on the algebra in a very inefficient way for a while before they got to something that we know today. So anyway, what we're going to do is we are going to use the cosine law and length of a line. It's amazing how much of what you do in grade 11 and grade 12 comes back to grade 10. I don't know if your grade 10 teacher talked about this, but so much pivotal math is taught in grade 10. Like in elementary school, you learn about integers and fractions, and those are big things, right? But then you don't do a lot of new stuff. It's just working on the same old stuff, number sense, and a little bit of algebra for a lot of years. And then in grade 10, you learn about systems of equations and trigonometry and factoring and start graphing quadratics. And those are like huge new steps into bigger mathematics, right? So the two key aspects of this are things you learned back in grade 10. So we're going to start with cosine law. Now you can either write this down right now or not if you want to just watch, but please watch. I do not want to see you tapping out and being on a phone. If you want to do that, you can go out and do that in the hallway, would be fine with me. Whoops, cosine law. Does anybody remember what the cosine law is? So be present here, but if you don't want to write it down, you can get it off the blog later, or classroom, whatever. Who remembers what the cosine law formula is? We're doing trigonometry units right now. It's related to trigonometry. It should be right there. Cosine law, c squared equals, it's not Pythagorean theorem, but it's close. Come on.
B squared plus A squared minus, I think 2 cos C.
Close. 2AB. Very good. Thank you for having a go at it. That's fantastic. Good on you. A squared plus B squared minus 2AB cos C. I forgot to talk about this. I got caught up in all the other mumbo jumbo. I wanted to talk about this diagram. So we're going to pause and go back to this diagram. Notice this is a unit circle. It is going through -1, -1, 1, and 1. Okay, so it's a unit circle because the radius is 1. That's important. This would work for any other circle. It's just a little bit simpler when we're using ones. That means these two lines here are both length 1. Agreed? Okay, and those we're going to call A and B, right? And then there's side length C. And this angle all the way here is angle A, which takes me to line A. And this little angle here is B, which takes me to line B, right? Is everybody okay with that? Should be pretty straightforward, which means this angle, which is important, is A minus B. So that's also could be considered angle C, because it's across from side length C. Like, see how this A is inside, but it's for the whole thing out here, right? Don't get confused about that. So this line, this angle connecting these two lines is C, which is also angle A minus angle B. If you don't get that, take a look at the diagram later, and you'll figure that out. Oh, and I will talk about this briefly. It's a little bit important to this proof, but not... you can just take my word for it if you need to. If this is 1, when I make my triangle, we've talked about this, this is X and this is Y. So the coordinates of this point would look like this. Okay, this would be coordinate X, right? Which is this X value here. So let me see if I can get this right. It would be of the related angle. It'd be like cosine of angle A is equal to adjacent over hypotenuse, which is X over 1, right? And when I take that 1 and multiply it on the other side, it disappears, which means the X coordinate just equals cosine of the angle. This is not something you've talked about a lot, and it might be something that you're not quite clicking with. It's actually a really neat thing to think about. That's another, we don't get into it a lot in high school, but it's kind of another important part of the unit circle, that coordinates on the unit circle. And for the same reason, y is sine, if you go through it. The coordinates of any point on the unit circle are just cos A sine A. And then if I increase the radius to like 2, it'd be 2 cos A, 2 sine A. Like it'd be easy to find coordinates on the circle. If that was a little bit too fast for you, don't worry too much about it. You might be something you want to think about at some point. Not going to be super important for how we're going to use compound angle formulas. Okay, so that all being said, I'm going to start subbing in here. C squared equals what was A? A is a length. It was 1. B was 1. And C is A minus B. Really important. I'm just going to simplify a little bit, and we're going to be done with this already. 1 squared is 1. 1 squared is 1. 1 plus 1 is 2, so that's 2. 2 times 1 is 2, so minus 2 cosine of A minus B. Done already. Yes? Lengths of the lines, like we just talked about. You tell me. What do you think? Somebody else answer that question?
Because it's in the circle, so it's 1 over the time. So it's point all 1, so any point on the circle would be 1.
Yeah, you want to add to that?
No.
Oh, okay, hold on, because I don't think Megan's convinced.
No, I just don't know what you would
This is a radius. This is the center of the circle. And this is a radius. And by definition, like we designed this circle to have a radius of 1. So any radius has a length of 1. So A and B are those lengths. Still don't look convinced. Okay, that's not important for right now. We can talk about that more after. That doesn't have anything to do with those numbers. Okay, Asia?
For the cos A equals A minus B, why don't we put 1 in?
Oh, those are angles. Kind of confusing. Sorry. Yeah, we should be using capitals or something. Maybe I should change that diagram, fix it. Those are the little a's. That's like algebra rule number 1. Don't use the same variable for different things. But these are side lengths, and these are angles. I guess this is a formula, and we use this. This is supposed to be capital C. Again, C is hard to differentiate. I'll make it even bigger, which is an angle. In my diagram, I use small letters for angles, but in the formula, we use small letters for side lengths, so it's kind of confusing. But anyway, does that make sense? Yeah, okay. Yep.
The A and B are the angles.
Yeah.
So should we change that to capital?
No. Because this now at this step, it matches the diagram, which is what we want. This is a formula. You probably noticed this, like the variables in a formula won't always match the variables in a question or in a diagram, like they don't have to, right? Pythagorean theorem: a squared plus b squared equals c squared. But if your hypotenuse isn't labeled c, it's labeled a, you still put that in. You know what I mean, for c squared, right? Okay, not confusing you. Okay, so that's cosine law. The other one, like I said, we're going to do is length of a line segment. This one I would be surprised if you remembered, but maybe somebody does. Does anybody remember the formula for length of a line segment from grade 10? Okay, I'll get us started. Big square root sign? No? X2 minus x1 squared. Starting to look familiar now? It's basically Pythagorean theorem. But my a squared, which is like a squared plus b squared, is the difference between the x values and the difference between the y values to get the lengths of these lines. So the length of this line and this line, right? Y2 minus y1 will give me this distance. X2 minus x1 will give me that distance. And so then we did between these 2 points. So this is the length of, or we're going to, sorry, we haven't yet. This is the length that we're going to look at. So we used cosine law to come up with an expression for C. And now we're using length of a line segment to come up with an expression for C. We've done that. We're going to do it in 2 different ways. And then you might guess what we do with it after that. So that is equal to x1 is cos A. So cos of A minus, and that was this coordinate. So this is where we are using those coordinates. But you can take my word for it that it's correct. And then if you want to know more about why, like if you want to spend some time thinking or talking about why, we can do that after. And then there's x2, right? So cos of B squared plus sine A minus sine B all squared, and it's still the square root of all that. Oh, and I should have changed that from L to C. So all I've done is subbed in. And for the record, it doesn't matter that these points are in quadrant 1 and quadrant 2, right? They could be any point. Has nothing to do with how I drew that diagram. The diagram can be drawn anyway. We haven't said anything specifically about those points. They could exist anywhere. We okay? So I'm going to square both sides, and I'm going to start expanding these 2 brackets inside. Okay? Again, we haven't done a lot of this kind of algebra yet this year, so you might be rusty, so this might go a little fast for you. But look it over, and it should be something you can convince yourself of. When we start polynomials in a couple of weeks, you'll be really good at this. So this is going to be, question? Yep.
Good question. So like over here, you're looking for the length of C, like here.
Correct? Yes, that's right. Yeah. Cos A minus cos B all squared looks like this. I'm going to do it over to the side. M squared minus n squared. Sorry, that's not right at all. M minus n, I was thinking about variables and not what I was actually doing, which is m minus n times m minus n. So that's m times m minus m times n minus m times n plus n squared. 2 negatives makes positive. Are we okay with this? M squared minus 2mn plus n squared. Is that okay? That's familiar. That's from grade 10 as well. Squaring binomials. So this is the quick way. So I'm going to use that here. So this is going to be cos of A all squared, which is cos squared A. Right? This means cos A all squared. That's the notation that means. Minus 2 cos A cos B plus cos squared B, cos B all squared. That's the first bracket expanded, plus the second bracket's the same. Sine squared A minus 2 sine A sine B plus sine squared B. Everybody okay with that? Come on, folks. Wake up. We square both sides. So see how C is squared now? And then we got rid of the square root on this side. And maybe we'd have to be careful of like plus minus, but it's a length, so we know it's going to be positive. So we're not too worried about that right now. Don't sit there thinking this is too hard, I can't follow what he's doing. You can. You got to push yourself. This is the first time you've seen this, but this is not hard. This is algebra that in this course should be easy for you with a little bit of thought, a little bit of practice. Anybody think they have an idea what we could do now? Layla? Yeah, how? That's a really good idea. I think if you look carefully, you're not going to see a lot of like terms because cos A's and cos B's are not the same. Cos A's and sine A's are not the same. This one's cos A, cos B. This one's sine A, sine B. I think you're going to be hard pressed to find like terms. So can we simplify in a different way? Possibly, but we're not going to yet. Nobody sees it? What if we rearrange? What's going on here? Ah, right. So cos squared A plus sine squared A. So I've got this one and this one. And then plus cos squared B plus sine squared B. So now I've got this one and this one. Minus, and I'm going to okay, I'll write it out the long way. Cos A cos B minus 2 sine A sine B. I think I got everything. So I got that one and that one. That's all of them, yes. Now do you see what we can do? Who's been practicing their identities? You got to stop believing this is something you're not capable of doing. Is 1. Very nice. So this is 1. What about cos squared B plus sine squared B? 1. Remember our identity, what's the word I'm looking for? Sort of techniques or ideas, like things that we use. Keep an eye on the other side. Look at the 2 that we had in that other version. And we just got a 1 plus a 1. And it's kind of starting to look like the other thing we already did. And I'm going to factor out these last 2. So minus 2 bracket cos A cos B minus sine A sine B. Whoa. Sine B. Okay, so I just common factored out the negative 2. Equals 2 minus 2 bracket, oops, too many 2's, cos A cos B minus sine A sine B. Done. That line is equal to c squared. That line is equal to c squared. So what can we say about them? They're equal to each other, right? If they equal the same thing, they must equal each other. So the first one is 2 minus 2 cos A minus B. And the second one is this line here, 2 minus 2 bracket cos A cos B minus sine A sine B. Subtract 2 from both sides. Divide by negative 2 on both sides. And we're left with this cos A minus B equals cos A cos B minus sine A sine B. Yeah. You're right. Thank you very much. It should be plus. Good catch. Which makes sense because that's the formula. Very good. So John, you missed all this, but it's pretty obvious when you look at it, right? Kind of, yeah. It's obvious that all of that's true. So this is our formula. It's called compound angle formula because this one is the difference between two angles. So I take two angles and I subtract them. The cosine of that is equal to the cosine of the first times the cosine of the second plus sine of the first times sine of the second. Like, that's the formula. So all of that proof is something you should continue to think about and understand. But the formula is what you need to memorize today and is what we're going to use to solve some problems. Any questions? So I want you to use this to find the formula for cos of A plus B. You do not need to do all of that work we did to derive it. That won't work. What you need to do is think about what you could sub into this formula to just turn it in to that. I'm going to give you a couple of minutes to think about it. If you can't get started, I'll help you. But I want you to think about it. And I'm seeing a lot of looks like I'm crazy. But this is something that we do every year with every MHF class. Like, everybody who's done this course before you, which is thousands of people, have done this and seen this, and they probably all felt like you at first, but if you work at it, you'll get it. And I'll remind you of a time, maybe in grade 10, when you were first seeing factoring, like for the first time, especially complex trinomial factoring. And your teacher did it, and it looked really easy for them, and you were like, what did they just do? And then you got really good at it. This is not out of your reach. Take my word for it. Like, in my experience, if you apply yourself, this is not even all that hard. It might be a bit different. It's not that bad. Okay, give it a try. How can we find a formula for cos A plus B? The first step is a really easy grade 9 step. Why is that true? So what if I told you you didn't have to do What could I sub in for negative b to change it to positive b? There's my quick hint. Think about it. Or use a different variable if you want, if that helps. This is, whoops, this is a little bit weird, but let b equal negative b. Then I get cos of a minus b, which is cos a cos b plus sine a sine b. And when I sub in negative b, I get cos a minus negative b, cos a cos negative b, right? See, not too bad, I hope. What's a minus negative b? Now this part is something that we've done. Does anybody know how we can simplify? Because we need to get rid of those negative b's. What can we do? What piece of knowledge can we use that we've gained already this year to get rid of those negative b's? Anybody have any idea? Looks like a couple of you are onto something. Jason?
Can we do negative cos b?
Why?
Because they're equivalent.
Why are they equivalent?
Can't remember it at the moment, but we did it 2 days ago.
Does anybody want to help with this? Okay, so first of all, is cosine even or odd? Somebody tell me. Definitively. Even? How did you get that? Like, how do you remember that? Okay, you just remember it?
Wasn't it if we were to flip it, it would still line up with itself?
Yes. Flip it how though? Like in the y-axis? Yes, that's a good. So visualization. One of the ways I think of it is the part close to the y-axis looks like a parabola. Parabolas are even. It's got an even exponent. So I don't know, like a memory trick, you want to remember that cosine is even. But what's the definition if cosine is even? Cos of negative x, or let's do theta, equals positive cosine of theta, not negative cosine of theta. Somebody help me out with sine. What is sine, even or odd? Odd, because it's the other one. And what's true of odd functions? Thank you. Very good. So cosine of negative b is actually the same as cosine of b. And sine of negative b is negative sine of b. And we're multiplying here, so I can bring that negative out front of the whole expression. I hope you're okay with that. So now you've got your two formulae for cosine compound angles. On the next page, you don't have to write them all down. There they are. Okay. The only reason why this is here, because we're going to derive sine and tan as well over the next 2 days. The reason why this is here is if you look at how similar cosine and sine are, they're similar but not the same. So this is cos A, cos B plus sine A, sine B. So the sign changes. This one's sine cos, cosine, and the sign stays the same, like it matches. So it sort of makes it easier to remember because they're similar, but it sort of makes it harder because you got to remember which one's which. So over this week, you really got to nail all three. Tan is different, but sine and cosine are very similar. So all you need to know today is cosine, but okay. So we've got our formulae that we need. Let's use them. How are we going to use them? Remember, I started out talking about how, like, the whole point of this is to be able to find the exact value of a new range of angles. So let's do it. Is 15 degrees, we're going to do 1 in degrees for your sake, but all the work we do is still in radians. So one example in degrees because it's going to make some thinking easier for you, that's all. A little illustration here. When we do exact values, We're talking special triangles. 30, 45, 60, and then multiples of 90. But the triangles are 30, 45, and 60. 15 isn't one of those. You don't get to just take it and divide it by 2 because it's half of 30. No, that doesn't work. So with compound angle formulas, we can find the exact value of the cosine of 15 as well. How do we do it? Well, can I come up with a sum or a difference of two angles that I can find the exact value of? And the sum or difference is 15.
45 and 60, or 45 and 30.
So get specifically, what would it be?
60 minus 45.
60 minus 45 gives me 15, or
Or 30, 45 minus 30.
45 minus 30 would give me 15. So a little bit of the exact steps might be different from one person to another, but your final answer will always be the same. You said 60 minus 45 first, so let's do that one. Cosine of 60, equals cosine of 60 minus 45. Do you agree? I haven't, like, those two lines are equal, right? 60 minus 45 is the same as 15. So cosine of 15 would be the same as cosine of 60 minus 45. And then we can use our formula. Has anybody memorized the formula yet? So it's cos of the first, cos of the second, change the sign, sine of the first, sine of the second. Doesn't matter which order you do the first, second in, but at least for me, it's easier to sort of structure it. What is the cosine of 60? Nope. I mean, for goodness sakes, you could use your calculator for this, right? But it's a half. What's the cosine of 45? Thank you. What's the sine of 60? And sine of 45 is the same as cos 45, 1 over root 2. Notice that my denominators are going to be the same here. 1 times 1 is 1 over 2 root 2. Root 3 times 1 is root 3 over 2 root 2, which is 1 plus root 3 over 2 root 2. I would encourage you, we're not going to do it right now, but I would encourage you at some point to check that on your calculator. You'll get a decimal answer, and then punch cosine of 15 into your calculator. Make sure you're in degree mode. You could do it for one of the radian questions instead if you want, and check that those are actually the exact, like the decimal digits. Convince yourself that worked. And if you've got your calculator for this, you can always check your answers to make sure that they're right. How do we feel about that? It's all right? Yeah? You like it better than the derivation that we just did? That feels more comfortable? Okay. Now, cosine of pi by 12. This is harder to turn into values that we can find the exact value of. This is harder to do because it's not as obvious to us. Like to put 15 in terms of 60s, 45s, and 30s was easy, but to put pi by 12, for a lot of people, they're not going to see it as easily right away. So I'm going to try to give you a little tip. Okay. What if I turn pi by 3 into by 12? What do I get? Yep, 4 pi by 12. Pi by 4 is? Say again? 3 pi by 12. And pi over 6 is? 2 pi by 12. So some combination of 4, 3, and 2 should give you pi by 12. But I'm going to add on to that. Any multiples of those. So 8 pi by 12, I suppose 12 pi by 12, that's unlikely to come up. 6 pi by 12, again, that's unlikely, but 9 pi by 12 sure will. 4 pi by 12 is already there. 10 pi by 12 possibly, right? So any multiple of any of those three are ones you could use, and they have to add up to this. So now can anybody see two of those that I can add together? John? 4 pi by 12 minus 3 pi by 12. Thank you. What is 4 pi by 12 or pi by 3? So this was 60. What is 3 pi by 12 or pi by 4? 45. Oh my gosh, this is the same question. What is pi by 12? It's 15. Anybody notice it's the same question? You already noticed that, some of you? Good for you. Right? It's the same question. We just did it in radians. Wasn't as obvious. That 60 minus 45 is 15. That pi by 3 minus pi by 4 is pi by 12. That wasn't as obvious. But when you think about it in terms of these special angles all over 12, and you start to practice and memorize those, and we're going to do this over 3 days. So if you don't practice, you're not going to be able to do this. But for the next 3 days, if you practice, you'll be very good at thinking in terms of pi by 12s. And if you were okay at doing it when you were graphing, that's going to help you now as well, right? So all these pi by 12s, and now I can see that 4 minus 3 is 1. And this is the same as, I'm going to do it in black, cos of pi by 3 minus pi by 4. So you want to write, and for now, absolutely, you have to write both of these steps, that step and that step. Write it down every time, and then we solve from this step. Don't try to solve from that step. Reduce them first. Do them in terms of 12. That's the easiest way to do it. Reduce them, and it's going to look exactly the same as this one. So let's move on to a new example. If anybody has any questions, that's good, but let's try this one. Deep breath, breathe. You're going to get through it. Don't worry. There's a lot going on today. You thought yesterday was hard. A lot of you are still probably thinking about that. Thank you. So 3 plus 4 gives you 7. 3 pi by 12 and 4 pi by 12 are two of those. Right? We already maybe starting to become familiar with this. So this is equal to cosine of 3 pi by 4 plus 3 pi by 12 plus 4 pi by 12, which is the cosine of pi by 4 plus pi by 3. You try to write this out from memory if you can. Should look like that. Change the sign, cos of the first, cos of the second, change the sign, sine of the first, sine of the second, right? Cos of pi by 4. Asia? Good, 1 over root 2. Last unit is starting to flood back, I hope, for some of you. It hasn't gone away. We still need to know how to do this. Cos of pi by 3. Cos of pi by 3 is a good one to memorize, because it's a good check on your calculator. It's cos of 60. It's a half, right? And if you've memorized that one, then sine of pi by 3 is the other one that you can get, which is root 3 over 2. And then if you flip them, you flip the answers. So then cos of pi by 6 and sine of pi by 6, you know what I mean? You can figure it out? Okay, so cos of pi by 3 is a half. Sine of pi by 4 is 1 over root 2. And sine of pi by 3 is root 3 over 2. So that's 1 over 2 root 2 minus root 3 over 2 root 2, which is 1 minus 3 over 2 root 2. You will see a lot of similar answers coming up over and over and over again. What root 3? 1 plus root 3, 1 minus root 3 over 2 root 2, those kinds of things, like similar answers are going to come up all the time. Yep.
For the second line, when you use like the long part of the equation, is it always going to end up adding like the special triangles?
These right here,
Yeah.
or these right here,
No, the other one.
like, yes, I mean, what doesn't matter which line you're talking about, these have to be in the special triangles because we can find the exact value of those. If I use two angles that I can't find the exact value of, how in the world does that help me? Right? It's just going to make matters worse. And so all the questions you're given will be able to be broken up into some special angles. So these will always be special angles. People are packing up, but let's try to get, we got 2 minutes. Can we figure out 5 pi by 12, even if we don't do the actual algebra? Can we figure out how to turn that into exact values? It gets harder when you have negatives or you have a 5 in there or something like that. What do you think? We're not allowed to do that right now. Very nice thinking, but don't ruin the question for me, Jason. Thank you. We could. Can we do it without negatives? Layla? Absolutely. How? What still will give us 5? Remember I said you can use multiples of these as well.
2 pi by 3 minus pi by 4.
2 pi by 3.
Oh wait, no, opposite way around. Sorry, pi by 4 minus 2 pi by 3.
What's the long version of that?
8 pi by 12 minus 3 pi by 4.
Very nice. 3 minus 8 will give us negative 5.
Did I say that?
I don't know. Cos, it's okay. We got it. Of 3 pi by 12 minus 8 pi by 12. But 8 pi by 12 is like 4 pi by 12, except it's not the same quadrant. So when we do this, we have to think about whether those values are positive or negative. I think I'm going to run out of time here, so unfortunately we can't talk about that. But if you're using anything other than one of those 3, you're in a different quadrant, and you have to take that into account. All right. Pick up the